So let's get to today's lecture. Dimension arguments. This is a useful technique, as I said, when the extremal problem does not have a unique, has many non-isomorphic extremal structures. Okay. So the first example we want to go through was this Erdős-Brein's theorem. We stated last time, so let me state it again. Let me say the idea again for this. So the idea is you have some so our goal is you have some collection F, a collection of some some objects, right? And our goal is to upper bound its cardinality. How many things in this family? And the idea is we're gonna find the injective map. This is into map to some low dimension vector space, such that the image of F, they are linearly independent. Such that the image of F linearly independent. Okay, because it's into, we know that its injection implies that the cardinality is the same as its image, no problem. But since the image is linearly independent, we also know that this is at most the dimension of the vector space. So as long as you can find a nice low dimensional vector space and a nice map into it, we can upper bound our family. We've seen one such examples, the odd town, even town problem. So let's see here. Let's recall the Erdős-Brein's theorem. The Brein's Erdős. It's about the results about projective plane. So if you have a projective plane, let me recall, for any set of points, P set of points in some projective plane, then the number of lines determined by P, this just means, I'll draw an example, this is P, right? And the number of lines determined by just, for every 2 points, it determines a line. For any 2 points determines a line, so you draw this line, right? Here's an example. Every 2 points determine the line. So the number of lines determined by the points set P is at least the cardinality of the set P, which let's use n to denote. So you have n points. Okay. Let me not specify. Yeah. This is the statement. So good. I want to say that by duality in projective plane, we can actually swap lines and points, the rows of lines and points. So this statement is also true, saying if you have a set of lines for L, which is set of lines in some projective plane. For L, a set of lines in projective plane, then the number of points determined by L is at least the cardinality of L. The same thing holds. All right. So if you want a picture, you have some set of lines. And what do you mean the set of points determined by lines? So here the set of points determined by lines means every two lines in projective plane intersect at exactly 1 point. Remember? So you take the points, the intersection of two lines. These are the points determined by actually these two also, right? Oops. These two lines should also intersect somewhere. Good. So the remark, did I make the remark last time when, yes, this, I'm just going to mention it here, but we will not prove it. We will prove a weaker version of this one. The remark is that if the equality holds, if the number of lines determined by points equals exactly the number of points, then either you have two cases, the equality holds, either when you yourself is a projective plane, the P, or you are this degenerate configuration. You can see here the number of points and the number of lines also n. All right. It's a degenerate case. Good. So let's come back here. Let's try to prove this one. We will actually prove the dual statement. The dual statement says for every set of lines in projective plane, the number of points determined by lines is at least the number of lines. And to do that, we're going to actually prove a combinatorial statement which implies this geometric statement. And the combinatorial statement is about a family of sets with restricted intersection. That falls completely into the theme that we are talking about. So we're going to prove a combinatorial statement about family of sets with restricted intersection. This is the statement theorem. For any for family of subset of n, okay. If they are pairwise intersecting, but they intersect exactly one place. If for any f not equal to f prime, for any two sets, we have f intersect f prime is exactly 1, then we have the number of sets in our family is at most the size of the ground set n. All right. So you see, this is quite similar, the hypothesis, to some of the things we've seen before. Requiring the pairwise intersecting, remember, if we don't put a restriction on the intersection size, just say that this is bigger than 0, we get 2 to the n minus 1 before. So now we require exactly 1 intersection. It drops quite a lot. Let's see how we prove this. Well, let's first see how it implies the dual statement, which is equivalent to the original statement. Okay. Because now let's think of the sets in F. This kind of sets in F are the lines in L. So you think of F to be L. Lines in there are the sets in here. What do we know? Every pair of sets, they intersect at exactly 1 point. So every 2 lines in our projective plane determine exactly 1 point that satisfy the hypothesis, okay, on the ground set of size n. Then the number of lines the number of lines is at most n. Okay. So this the number of lines is the L here, and the number of points determined by lines is the ground sets. Let me write it down. This implies the dual statement. Of the prime Erdős, because we may assume in the above theorem every point in N is in at least 2 sets in F, right? If it's not in 2 sets, simply removing it from the ground set and from all elements in F, you will not affect this intersection hypothesis. Otherwise, removing it. Okay. Now, every point in at least 2 sets is the same as every point is determined by some 2 lines. Then that's the dual statement. Now, F is the set of lines and the ground set, and is the point determined by F, which is L. All right. So let's see how we prove this pure combinatorial statements. Forget about the geometric statements. Okay. We said it's gonna be dimension argument. So we want to map it to some vector space linearly independently. Linear independently. Proof. This one is actually quite simple. So what we're gonna do is let's look at the incidence matrix. So consider the incidence matrix of F. So what is this? What it means is the columns is the ground set and the rows are the elements of F. Let's say F equals 2. You have M elements in there. Look something like this. So the rows are the sets, right? And you put the 1 there. So the ij's entry equal to 1 if the element j lives in the I set. This is just the incidence matrix. This is a m by n matrix. All right. So now if we can prove the row, so naturally each set in F correspond to a vector in Rn, right? So each set Fi in F, we write it as a 0, 1 vector, nth dimension. If we can prove these vectors, their indicator vector are linearly independent, we are done. So if, how do I write their indicator function? Let me just write Fi, shall we? The indicator function of Fi are linearly independent, then we know the number of such sets, which is M, the size of the cardinality of F, is at most the dimension, which is N. Then we are done. Then that means F is at most dimension, which is N. So let's see if they are linearly independent or not. So that means let's look at some scalar alpha I times Fi. Let's look at the linear combination of them and try to see how this look like. Okay. I goes from 1 to m. Let's call this guy vector x. To understand this, let's look at its norm, the inner product. So if you look at the inner product with itself, what is this? Okay, which equals to linearity alpha I, alpha j, fi, fj. Okay, but what is fi, fj? Fi, fj equals to, if I equals to j, that's easy. You just, the same set. The same set, you have ones at the same position. How many ones? Well, the size of the set. So if they are equal, this is just the size of the set Fi. If they're not equal, what do I know? I know there's, I know that these two sets, they intersect at exactly one element. That means there's only one position they share one. The other positions, when they have one, the other one must have 0, meaning the inner product of their characteristic vector is exactly 1. So this equals to 1. No problem. Let's plug in there and see what comes out of that. So we have this guy equals to, let's look at the diagonal term first. Diagonal term alpha I, alpha j becomes alpha I squared, 1 to m. The inner product of Fi with itself, as we said, is the size of Fi. Now, what's the cross term? The cross term is I not equal to j. Alpha I, alpha j, times the inner product, which now is 1. So times 1. Let's, what would be nice is we want to say this guy when it equals to 0, right? Suppose this equals to 0, then we want to say each, oops, where did I go? If you have a linear dependence, this equal to 0, each alpha I needs to be 0. Here, this is non-negative, that's nice, but this is not non-negative. Let's do some transformation. So let's do it on the side. What's this guy? Well, This is all, we all familiar, this sum of square. Sum of square equals to what? Equals to the square of everything plus the cross term of every pair. That's precisely I not equal to j, alpha I, alpha j. Okay? So that means we can write this guy as the difference of this minus this. Then we can merge this guy in here. So we have this equals to sum of alpha I squared fi minus 1 plus sum of alpha I equals to 1 to m squared. Now, very good. Assume for a moment each fi is of size at least 2. For a moment, let's assume it's at least 2 size. Then we are done. Why? This is not negative. We can throw it away. So that means this is 0 if and only if. So this is not negative. And this is positive when this is at least 2. That means it's 0 if and only if every alpha I is 0. What does it mean? If you have a linear dependence, there's no linear dependence, basically. If this is equal to 0, all alpha I must be 0. Linear independence. And we are happy. That's what we want to prove. So what happened when fi is some fi is 1? That's also easy. If, say, f1 is 1, but then we can analyze it precisely. If f1 is 1, how possibly can it look like? Let's say, without loss of generality, f1 is the first element. Okay? Singleton. What do we know? Every pair of sets, they intersect at exactly 1 point. So that means all other sets, fi, 1 must be in there for all I. First of all, because every other I must intersect f1 at exactly 1 element. But also, since 1 is in fi for every I, then fi, fj, apart from 1, they have no common elements, right? And fi intersect fj is 1. So that means apart from 1, they are disjoint. How many disjoint sets we can pack into the remaining elements apart from 1? You just take all the singletons, right? So fi minus 1, they are pairwise disjoint. Implies at most m minus 1 of them. This I is from 2 to m. That finishes the proof. Okay, and from the last part of this proof, we can also see this theorem, the remark, the bound is tight. And the tight example, for example, you can have 1, 1, 2, 1, 3, right? You minus 1, you pack everything singletonly. Da da da, 1 n. Pairwise share exactly 1 element. There's another example correspond to when each one is at least 2. You can simply replace the first one by 2, 3 to n, and have 2, 3 dot 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 to n, and the rest the same. If you think a little bit, this guy is kind of like this pencil thing, right? It's kind of 1, 2, 3 dot, 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 to n, isn't it? Any question? Okay. Very good. So this one is a simple example of dimension argument. We don't even need to find that. We don't even need to find some clever map so that the linear independent will simply just look at the characteristic vector of each set in our family. And they are already linearly independent, living in a dimension n vector space. Done. Next example of dimension argument is set of points in the plane, not in the plane, in Euclidean space, such that if you look at pairwise distance, you only get at most 2 distinct distances. If you have a set of points where the pairwise distance between them, if there's only one, this is the R2 case, or R3 case, if I draw maybe like this, such that the pairwise distance is exactly the same. So only one distance. When there's only one distance, one same pairwise distance, a set of points, then this P, then P is at most n plus 1. You cannot have, for example, in the R3 case, at most 4 points. That's easy to answer, and this bound is tight. Because you can take a regular simplex, like this tetrahedron, regular simplex. Okay. But when we allow 2 different distances, how much bigger can a set be? That's what we want to know. Question. What if we allow 2 distinct distances? Let's first think of some lower bounds. What's a good way to construct a set of points in Rn with many points? But the distance between pairs of them can only take 2 different values. Okay. One way to think of them is it's always good to discretize things to think of 0, 1 vectors. So if you think of in Rn 0, 1 vectors, if your 0, 1 vector only have 2 entries of 1, then the distance is basically the same as Hamming distance, where how many entries they differ. So if you have 2 1s, their distance is either 4 all three, right? They either disjoint, then distance is 4, or they not disjoint, then distance is 3. No other cases. All right, so let's make it continuous. In other words, in Rn, we can take EI plus EJ, where EI are the standard basis, is 0, 0, I. Oh, no, I, 1, I mean, at the i's position. For ij in n choose 2. For every pair of coordinates, you can sum up their standard basis in that pair direction. Now, this is your set of vectors, which correspond to this case. Pairwise distance, take 2 distinct values. The size of this set is n over 2. So the maximum size, so my question is, maximum size of the set P, which allow 2 distinct values, is at least n over n choose 2. We grow from linear to quadratic. The question is, what about upper bound? We know we can do at least n choose 2. Can we get some upper bound that's not so far from it? And we don't know the answer of the exact maximum, but we do know this is quite close to the truth asymptotically. So we can prove the best upper bound, here's a remark, best upper bound is n plus 2 choose 2, very close. This is by Block-Weiss. We're going to prove something slightly weaker, but easy to state, easy to prove. Theorem, let X, you have a set of points in Rn, a set with at most 2 distinct distances between points, pairs of its points. Then we get the upper bound. X is at most 1/2 n plus 4 n plus 1. Almost like these bounds, just a little bit, leaving all the terms the same, right? So is the statement clear? We have a set of points in Rn. Pairwise distance, take 2 values. We want to prove this quadratic upper bound on the set of points. There are not so many points. As I said, our idea is to map X nicely to some vector space. Or in other words, associate some vectors of polynomials to each one of these elements in X so that they are linearly independent. And the space we live in, this point, this in vector space, we can bound this dimension. So we're going to use this map proof. Let's give names to the points in X. Let X to be, let's say there's T points, which is V1 to Vt, V2 to Vt. And let's let capital D and little d to be the 2 distinct distances between pairs. Distinct distances. Now we're going to associate or map associated to each point vi in X the following n-variate degree 4 polynomial. PI, I call it PI. Okay. So PI of X for all X in Rn equals to, you just take their distance, look at the distance of X to Vi square minus D square times X minus Vi distance square minus capital D square. Here, I use this norm, I mean the little L2 norm. So this is basically the little L2 norm. It equals to the Euclidean length. That just means the sum of ui squared, I goes from 1 to n. You take a square root of that. Okay. You can already sort of see why this is defined this way, because now the claim is that pi I in T ranging over all points in our sets, their corresponding polynomials, they are linearly independent. Okay, let's see the proof. Not so hard, standard to verify. Notice first that Pi, if you look at Pi Vj, what is this? If I equals to j, so if plug in Vi, if you plug in Vi, this is 0, this is 0, we get non-zero, which is non-zero, some value. I write it down. What's important is that it's non-zero. But if you plug in some point that's not Vi, Vj, j not equal to I, look, Vj here, then this is exactly the distance between some pair of points in X, which can take value either little d or capital D. That means one of them becomes 0, and the product will become 0. You get 0. So you kind of have this, you see, you have P1 to Pt, you have 1 dot 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 V1 to Vt. This is a diagonal matrix. Okay, this is non-zero. Non-zero, yeah. They are linearly independent. Let's prove it. So if you have linear dependence, let's say if alpha I pi equals to 0, then you plug in for every j in T, plug it in, let's see, 0 equals to sum of I alpha I pi Vj. As I said, if I not equal to j, it vanish at the pi. So the only thing when we plug in Vj, it does not vanish, is for Pj. So you have alpha j Pj Vj. But we know what's Pj Vj. It's d squared, d squared. This implies alpha j equal to 0. So all this must be 0. They are linearly independent. Good. All we need to do now is to say, okay, the space they live in where has low dimension. This is n-variate degree 4 polynomial. If you collect all degree 4 monomials, there are big O of n to the 4 of them. right? Something like this. But that's quite far from where we're at. We need to get a quadratic bound. So we need a more economic way of spanning these sort of polynomials. Okay. So let me write it down. So immediately we get S degree 4. We can do much better. We need to find a more economic way set of vectors spanning PIs. Okay, so let's see how PIs look like. Let's just look at one factor. This is symmetric. Let's look at one factor. So a factor, write it out, x minus vi squared is the sum over Rj in n coordinates xj squared minus 2 xj vi, the j's coordinate of vi points, plus vi's norm, so which is this guy. Okay. So you see, even though this is degree 4, but this two looks almost the same, and this sort of polynomial can be spanned by the following thing, which is this implies pi HPI is a linear combination of the following polynomial. What? First of all, let's capture the leading term. We have two things multiplied together, right? So the leading term is this guy multiply itself. We need a separate one for it. xj square, take a square. Okay. That's the sort of diagonal term. Now you should have this guy multiplied by this guy, right? So we have, how does this guy multiplied by this guy look like? You just need to take this times this, ranging over all n. So there's only one of them. This is x k times the sum of xj squared, where k is in n. So there are n of them. All right. This times this is done. We should have we should have this times itself, right? This times itself, we should always view this as constant. This is constant. So this times itself is basically xj xk. So we have xj xk, where I less than j less than k, and the number of such thing is n plus 1 times n over 2, right? The distinct ones is n choose 2, which is n minus 1 times n over 2, plus the identical ones, xi squared, which is n of them. So flip plus minus 1 to plus 1. Cool. Okay, this time this we are also done. This time this done. We should also look at this guy times this guy, which is just a linear term on each xj. So we have xj, j in n. This is also n of them. Finally, we should have constant term. So the constant term one of them. Sum them all up. We have the dimension of the space containing all pi is at most this sum up our desired bound, which is m plus 4, m plus 1 over 2. We are done. Any question? Okay. So, good. This example. The next thing we want to see is families forbidding a single intersection size. It's a famous theorem by Frankel and Wilson in the 80s. So we have 2 to the n has size 2 to the n, right? This is the size of the family of all subset of n. This is our universe, at least the universe we've been working for now for a while. And while putting on pairwise intersection pattern restriction, the size will get smaller. Recall, if you want it to be pairwise intersecting, we get 2 to the n minus 1. So you shrink by 50%, by half. That's not so bad, constant loss. And even in the uniform setting, we have Ehrlich-Corrado saying you are at most n minus 1 choose k minus 1. But if, let's say, k is n over 2, half of it, this is just 1/2, n choose n over 2 is easy to compute. Yeah. But what is this size? This is the middle layer of the hypercube. Using Stirling's formula, this is roughly the whole size just divided by square root n. Now we are a lot smaller. You lost some factor, but this factor is still not exponential. You are still almost everything in a sense. Exponentially, you are as large as the original everything. And here, intersecting means we're forbidding a single intersection size 0. We don't want them to be disjoint. This is intersecting is the same as forbidding 0. Intersection size 0. Okay, so that means forbidding a single value of 0 for pairwise intersection size is not affecting too much of how many we can put into this family. Somewhat surprisingly, forbidding some other values will drastically decrease the maximum size by exponentially, in fact. Okay, we should see. Here's Franco Wilson says a single forbidding size could force the family to be exponentially smaller. So let me state their theorem. Take P to be an odd prime and F, we have a family of sets. Now suppose we have two conditions. The cardinality of every set in our family is divisible by P, is a multiple of P. Wait, let me check. Does it need to be odd prime? Maybe it's... I'm not sure if we need it to be. Why I wrote odd prime? Okay, so please check yourself afterwards. I think maybe this is not needed. Check it. Just take some prime. Now, good. Every set, its cardinality is a multiple of the prime P, but their intersection is not a multiple of the prime P. So for every F, not F prime, in F, distinct ones, their intersection is not 0 mod P. Maybe I should just use 2 bars. Mod P. Then the family cannot be too large. At most, n choose 0, n choose 1, dot, 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 n choose P minus 1. Okay. Stated like this. So for example, if you take P equal to 2, what do we get? This is like a variation of odd town, even town, right? If you take P equal to 2, a collection of sets, every club is even size, but the intersection is odd size. It's like you swap the role of odd and even. Then the bound you get P equal to 2, you just have this first two term. It's n plus 1. So not so far from the tight answer, fairly close. You get at most n plus 1. Fairly tight. Fairly close to truth. An interesting case is, let's take n equals 2. Let's consider n equal to 4p, let's say. I take p to be a quarter of n, the ground set size. Now I have some collection of sets where I require its size to be divisible by p. That's not so hard. I just take the middle layer. Middle layer is of size n over 2, which is equals to 2p. So it satisfies the first condition. And consider f, which is in n choose 2p, the middle layer. So the first condition is satisfied. And this middle layer has size n choose n over 2, which you are not losing much, right? Not losing much by passing to the middle layer. Now we are forbidding a single intersection size. You don't want the intersection of two sets of size 2p. You don't want them to be 0. So being 0, then the only two possibilities is 0 or p. Okay? Here you say, okay, we are not forbidding a single one. Actually, we can forbid 0 easily. Just take an intersecting one here. And by Erdős-Corrado, intersecting one, consider an intersecting family F in here. Okay. Then we are only forbidding intersection size P. By this, we get the size is at most sum of P minus 1, I from 0, n choose I. This is roughly n over n choose 4. P is roughly n over 4. That's exponentially smaller. This is roughly 2 to the n times some entropy function of 1/4. This you can compute. It's 1 minus some c times n, exponentially smaller, forbidding a single set. All right? Forbidding a single intersection size. Good. So how do we prove that? This theorem? Any question about the statement? Okay, if there's no question, I will move on to the proof. Once again, the proof is I want to associate to every member of F some objects in some low-dimensional vector space so that it's injective. So the image is the same as F size, and they are linearly independent, so we can upper bound it by dimension of vector space. Proof. We will associate now an n-variate polynomial of degree p minus 1. Let's call it P sub F over the field FP as follows. For each x in Fp to the n, you define PF of X to be 1 minus, okay, the inside here is the sum of xi, I in f, raised to power p minus 1. This is the polynomial. Obviously, it has n variable, x1 to xn. And degree p minus 1, good. First thing we have to prove is, for this choice of map polynomials, this collection over all family, the sets in our family, they are linearly independent. Let's prove that. Claim is PF linearly independent. This is also not hard to verify. So what do we know using our hypothesis? You take two distinct elements, you take two elements in our set. Their intersection size is non-zero mod p when they are different. When they are the same set, the intersection is just the cardinality of the set. Then it becomes 0 mod p. All right, so let's write it down. Proof. By hypothesis, for any f prime in f intercept f prime equal to 0 mod p if and only if f and f prime are the same. So we can then compute, we can evaluate each polynomial at the characteristic vector of every set in our family. That equals to, let's write down by definition, 1 minus. So what is this plugging here? 1 f prime. We get 1, we add 1 whenever f and f prime has a common element, otherwise 0. So what's inside is precisely the intersection size of f and f prime. Raised to power p minus 1. In finite field, Fermat's little theorem says every element in the finite field raised to power p minus 1. If for every non-zero element raised to p minus 1, write it. So let's first look at f equal to f prime. If f equal to f prime, mod p, everything is done by mod p, this becomes 0. Okay, so you just have 1. If f not equal to fp, f not equal to fp, then this is non-zero. Any non-zero elements raised to power p minus 1 is 1 by Fermat's little theorem. Okay. Mod p. Good. So you have the from here, again, we arrive to this case. Remember, you have PF1, PFM, you have rec F1, FM, you have this diagonal matrix. They are linearly independent. The rest of the proof is the same as what we did here. I will leave it for you to prove. Where is it? Here, remember? We construct this, and you find a way of evaluating them. You get a diagonal matrix. then they must be linearly independent. Okay. Good. So now all we need to do is to estimate the vector space containing all these p polynomial. This is degree p minus 1. So all element looks like xi. So if I look right x, right? X to the alpha, where alpha is also a vector. Alpha 1 to alpha n. This just means x1 to the alpha 1, x2 to the alpha 2, xn to the alpha n. What do we know? We know the sum of all alpha i's at most p minus 1 degree. But the number of such polynomials, there are just too many. We need an additional trick called linearization, the multilinearization trick. So need additional trick. One trick, multilinearization to reduce dimension. So what's the idea? The idea is simple. We have proof already evaluating the point where we evaluate to see the linear independence is 0, 1 vectors. Okay. Note that the point we use to evaluate to show independence, linear independence, 0, 1 vectors. Over 0, 1 vectors, any monomial, let's say x1, 3, x2, 4, x3. Today is 2024, May 16. Any monomial like this has the same value as you just made the power be 1, right? Since you just plug in 0, 1. So it's the same if you just smear the power off. That means if you just simply get a new polynomial where whenever you have xi have some non-trivial power, at least 2, you just replace it by a single term, a linear term. Then you will not change the evaluation over the characteristic vector sets in the family. In other words, if you do this so-called multilinearization, that's exactly this process is, the new polynomials we obtained are still linearly independent. So replace in PF all powers xi to the a at least 2, just simply by xi, we get new polynomials, PF, let's say prime, still linearly independent. And that's the polynomials we actually going to work with. Okay, so this new set of polynomials, what's good about it is every monomial appearing in it, all the power is 1. So the number of monomials we need, you just need to see what index appears. And the number index of coordinates that appear is at most p minus 1 because it's degree p minus 1. Like multilinearization do not increase the degree. So still degree at most p minus 1. And these new multilinear polynomials are spanned by at most these many monomials. And we are done. This means constants. This means x1 singletons xi. This is xi, xj, dot, dot, dot. You choose p minus 1 of them, so on and so forth. Any question? So sometimes some first choice, it doesn't really quite work out. You can still use some trick. I will see some additional tricks like linearization, making a multilinear polynomial if the evaluation point where we use to prove independence are 0, 1 vectors. We can do that. And oftentimes, that's the point over which we evaluate. Another trick is here in this two distinct distance problem, where we have set of polynomials which has some good symmetry, then naively using the dimension is not so economic, and you can make use of the symmetry to find a more a cheaper way to span them. That's another trick we're seeing here. The time is almost up. I will wrap up today's lecture here. So again, all the problems in the final will be the material from lecture 1 to lecture 21, which is today's lecture. So up to today's lecture, everything examinable. From next week, the plan is from next week on, the material will not appear in the final exam, but still they are important. My plan is to finish this dimension argument by presenting an application of Frankel and Wilson in combinatorial geometry. And then we move on to methods. Okay, we have about 7, 8 lectures left. Any question about today's lecture?